So the reason you haven't learned the Lagrangian formulation of quantum mechanics before is that these path integral calculations are actually quite difficult. The technique is hard for what you might call normal quantum mechanics, the kind of quantum mechanics you've done, but it's often better for relativistic quantum mechanics and particularly perturbation calculations in quantum field theory such as quantum electrodynamics or quantum chromodynamics. It's also very clear from here how we get classical mechanics out of quantum mechanics. Now note that here all paths are equally important, so there's no sense in which the least action, the path with the least action, is special in any way. But it still turns out to be very important for reasons I can explain. If we parameterize the paths, we have these purple paths, if we have one of those being the least action, and we're going to take one of the points here and we're going to move it, so instead of being the least action it's going to have some little discontinuity, then we can sort of plot on an axis all those possible paths. Now in fact, we're going to need to parameterize all the paths, and so a simple two-dimensional plot like this won't work. But if we look at that, then the point where we have the least action is just going to have some phase. So if we look at the real part, it's going to have some value. And then the action is going to go up on both sides, and so it's going to start to oscillate differently. And then as we move that point, it's going to oscillate faster and faster because the paths are going to be more and more extreme. And they're going to oscillate with exactly the same amplitude. So the amplitude envelope here is exactly constant. I haven't drawn that particularly well. You can kind of imagine that the amplitude is really constant, but the phase is oscillating wildly. This kind of integral is in fact exactly the kind of integral that we just solved, and we realized that in fact where it's oscillating wildly doesn't actually contribute to the integral very much, because where it's oscillating really wildly, we've got positive and negative bits cancelling each other out. So the only really important parts of this wave function are the ones near this inflection point. And remember, this inflection point is the path of least action. Now to do this integral properly, of course, you have to perform this integral and you'll get a particular value. And if you have complicated structures and complicated paths and potentials, then you might need to do all sorts of calculations to get it. But in the classical world, where you have the path of least action, the natural sort of scale for this action is h bar, and h bar is a very, very small number. And so very, very tiny deviations from that path of least action are going to put you way into this oscillatory regime. And so only the paths incredibly close on a kind of quantum scale to the least action are going to be relevant. And that's why the principle of least action is an emergent property of quantum mechanics.